Okay. So welcome back. So now we're going to have a very physics talk by Pierluigi Niro, who's telling us about symmetry breaking 3D QED. And please, Pierluigi, go.
Thank you, Edo. So let me thank the organizer for inviting me here. This nice kickoff event. So as Edo said, I'm a physicist, so this talk will be a lot about physics, not about mathematics. So, but please interrupt me at any point if you have any questions. I'll try to go slow at the beginning, and then maybe the second part more technical for the experts. So this talk is about symmetry breaking in the three-dimensional version of quantum electrodynamics, which is the theory of electrons and photons that we know that in 4 dimension governs our universe. And it's based on a recent work that I did in collaboration with Thomas Dumitrescu and Ryan Tongren, who are faculties at UCLA. And there is also a very closely related work appeared around the same time by Chichester and Zorko Margotsky, and they arrived at the same conclusion with a different approach. And then if I have time, I will also talk about some supersymmetric version of this story, which is a work in progress with Thomas and Kenny Trivigator, who is a faculty in San Diego, and Orsella, who is a postdoc at EPFL in Islam. Okay. So let me try to motivate why we're doing this. So, because of course, as you know, we live in a 4-dimensional world. So the first question you can ask, maybe not a question that the mathematicians would ask, but is why you're doing this. Okay, so the reason is that if you take a statistical system at thermodynamic equilibrium, so in ordinary 3-space dimension, and this is actually described in the continuum limit by a 3-dimensional quantum field theory. So instead of describing the dynamical field theory of our 4-dimensional world, which is the one that governs the experiments at accelerators, here we are describing systems that are equilibrium and that you can simulate in a lab. The important thing is that usually we are used to condensed matter systems that are described by spin systems. So you discretize space and time, as much as in the Lane model that we saw before. And the fact is that when the correlation length of this object of this system go to infinity, which actually means it's much larger than lattice spacing, so these the fine details of the model do not matter anymore, and the system is supposed to be described by a continuum field theory. Right? So this is more phenomenological interest of this story, and from more high energy perspective, is that if you consider an ordinary 4-dimensional quantum field theory at high temperature, this means that you take your 4D space and you compactify one direction on a circle, and the radius of the circle is the inverse temperature. So when you go at high temperature, basically this system is described by a quantum field theory in 1 dimension less. And so this is another possible interest of 3D quantum field theories. And then there is a more formal interest of these theories, is that, okay, if you're not familiar, if you consider gauge theories in 4 dimension, like the standard model and the theories that describe our universe, they have a property which is such that the coupling, you don't know if this coupling grows or in the UV, so at short distances, or grows in the IR, so at long distances. You need to perform a computation, which is highly technical, in order to understand what is the fate of this coupling, of the interaction. But in 3D, this is not the case. In 3Ds, all gauge couplings have the properties that at very short distance, they are weakly coupled, but at very long distance, they are strongly coupled. Okay, so it means that one of the most interesting properties, which is a strong coupling, is already visible at the classical level in 3-dimensional theories. So they are also a useful playground to study these effects. And okay, the theory I'm going to focus on is called QED3, so quantum electrodynamics. Is what? It's a U1 gauge theory. This means just Maxwell theory, right? Like the photon, which is described by this Lagrangian here. And you couple to this the charge 1 Dirac fermions. So they have charge 1, the electric charge under the gauge group, and you have an F species of them. And we'll take an F even for reasons that will be clear later. And this is the Dirac Lagrangian. So this is how you write the actual system. And this is the mean coupling between the gauge field and the current side bargain on the loop side. Okay. This statement is that the gauge coupling, like the electric charge, is squared, and this means that the dimension of this object is 1, which is another way, a short way to say what I was saying before. So the infrared, this theory is strongly coupled. Okay. So if you want to write the same thing in 4 dimensions, exactly the same, just you'll be in 4 dimensions, the properties will be completely different. Okay. Okay, let me go to something that okay, let me do some remarks about the conformal window. So the theory that describes the strong interaction is called quantum chromodynamics, so QCD in 4 dimensions. This is similarly a gauge theory. So it's made of the gauge group is SUN, it's not U1, and then you have NF fundamental Dirac fermions. Okay, this is the theory that describes quarks and gluons in our universe. And then you can say, okay, what happens if I vary the number of species of fermions? If I put a lot of them, okay, more than some critical value that depends on the rank of the SUN gauge group, then this theory is infrared free, which means that the coupling at long distances goes to at long distances goes to 0. So it's a free theory, and you can use perturbation theory. Then when NF is smaller than this critical value, the theory is actually strongly coupled, which means that the coupling goes to 0 at high energy, but goes to infinity at low energy. And now you can ask yourself, okay, what happens? What is the fate of this theory below this threshold value? And what people believe is that there are 2 phases. One is called conformal window, which means that the theory in the infrared goes to a quantum field theory, which is actually a conformal field theory. So it has an enhanced space-time symmetry. And but this behavior is supposed to be described only till some value, NF star, below which the theory enters in a different phase, which is a so-called symmetry breaking phase. So here I want to emphasize that there are 2 different questions. One question is, what is these values of NF star as a function of NC, right? How much is this? And this is a question that has no answer analytically. Okay, it can only be investigated numerically. And the recent simulations show that for NC equal 3, okay, which is our word, it's supposed to be between 9 and 12. Okay, whereas this number for NC equal 3 is like 16. And but the second question is, okay, suppose someone comes to me and tells me, okay, there is a critical value of an F such that this conformal window ends. What happens below that? Okay, so the theory is not a conformal field theory. Conformal field theory just means that it's scale invariant, basically. But something else happened, and it has been proven in the 70s by Toth that what should happen is that the global symmetry of this theory, which is this here, SUNF left times SUNF right times U1 vector, is spontaneously broken to some subgroup via the condensation of the fermion. So this fermion, psi is a gauge invariant object that condenses, and this breaks the symmetry according to this pattern. And if you're familiar with symmetry breaking, every time that you have symmetry breaking, you have massless particles, which are called Goldstone bosons. And the Goldstone bosons of this breaking are the pions that you measure in experiments. Okay. Now I want to.
Sorry.
Yes.
Since
yes.
In this context, should we think of it? I think a real world as 2 or 6. Like, is it light quarks that we care about, or all quarks, even if they're heavy?
Well, I would say NF equals 3.
NF equals 3.
Yeah. The 3 lightest quarks. There's a huge hierarchy between the first 3 and the other 3 families. Yes. But this, in principle, is a question that. I want to analyze the phase diagram, thinking NF as a function, and also NC. Sure. The real world is at both 3, or if you want, this is 3 and this is 6. Yeah. Okay, now I want to ask the same questions, but in the context of the simpler context of the abelian gauge theory. So as I said, now everything is easier because you don't have SUN gauge group, you have U1, but you still have NF Dirac fermions. And okay, what happens now? So as I said before, there is no regime where the theory goes to an infrared free phase, where the coupling goes to 0 in the infrared. So there is this green region is not present in 3 dimensions. So the conformal window actually is a semi-infinite window. So you start from very big NF. There is a conformal field theory on the way. There is an NF star, and then there is something below NF star. Now again, I can ask the same 2 questions. So one question is, what is this value here? And exactly as in the case here, there is no analytic answer to this. So nobody knows how to do a computation to prove this. But there is the bootstrap method that are the most impressive on this issue that tell us that most probably NF star is between 2 and 4, which means that I'm only considering even NF, so which means that most probably NF equal to 4, 6, 8, and above, they are conformal field theory, but NF equal to 2 is probably not conformal field theory. Okay, so it does something else. And the question I'm going to focus on today is, okay, what happens here? Okay, let's fill in these dots. Let's suppose someone goes to me and tells me, look, there is an F star somewhere, and then my task is now saying, okay, what happens here? And you could just copy paste this answer, adapting to the 3D case, which, well, it's a bit more sophisticated, but this would be the answer, that you have an SUNF symmetry breaking in this way. Still get a condensation of the fermion, but this I'm going to argue that is a wrong answer, and the correct answer is slightly more sophisticated. Okay, questions?
So what's the definition of NF star?
NF star is the critical value of NF, such that at long distances, the theory is not scale invariant anymore.
Okay.
It's not like conformal field theory means like a second order transition, right?
The question is, you know that there should be a symmetry breaking, but you don't know how the symmetry should work.
Exactly. You don't even, in principle, we are agnostic even on the symmetry breaking. We now want to classify all the possibility and show the story would be that I will tell you at the physicist level of rigor that there are only two possibilities. Either is a CFT, but I'm excluding this by hand because I'm interested in this region, or there is something else, which would be a symmetry breaking, but not of this form. Right? And the point is arguing that that's the only plausible answer. All right. Okay, so maybe let's review do a crash course on quantum field theory. For those of you who don't remember or never remember. Okay, so let's talk about free photons, okay? Nothing else, just photons. So this is the Lagrangian. This is the Lagrangian, F is a field strength, A is a U1 connection. So the global symmetry of this theory is called U1 magnetic, okay? And the current is just the field strength itself, the star of the field strength, the dual of the field strength. And this is automatically conserved by the Bianchi identity, because dF is equal to 0, so this is automatically a conserved current. And then you can ask, okay, what are the operators that are charged under this symmetry? And these are the so-called monopole operators. And monopole operators are a bit complicated because they are disorder operators, so you cannot write them as a function of your fundamental field A, but they are written as boundary condition in the path integral. Roughly speaking, what you want is that you want a configuration that fills some magnetic charge, right? Now, F is a dA, right? So if there was no singularity, the integral of F would be 0, for reasons that you know better than me. So what you have to do, you have to remove a point from space-time, right? Then you have to take a sphere, S2, and impose that the flux of F over this S2 is equal to 2 pi q. Okay? And this will give a monopole charge to this beast. Okay? And these are the objects that are charged under this monopole symmetry. Now, this is very complicated to understand. So what you can do something different, and you can prove that this theory can be actually dualized to a theory of a free scalar. Okay? You can play and trick, and actually these theories are completely equivalent. And this is a much simpler theory in which you just have a scalar field, so no indices. And well, right, if you're doing classical mechanics, this would be just Q dot square, right? And this is the same thing. And sigma is a compact variable, so it's like 2 pi periodic. And now, what before was this complicated magnetic symmetry, here it becomes the shift symmetry of sigma. So I'm free to shift sigma by any constant I want, and the Lagrangian does not change because it only enters with the period. And so it has a current, but now you can write what are the objects that are charged under this symmetry, and it's just the vertex operator for this sigma, right? You write e to the I into sigma, then you shift sigma by something, you go sigma is sigma plus c, and this goes to itself times a phase, right? And this phase is in 0. This C is in 0 to pi, right? Because there is a 2 pi identification, so these are U1 symmetry. These are the monopoles operator that are charged under this. And now you see what is the fate of this symmetry is that this symmetry is broken spontaneously, right? Because there is no potential for this sigma here. So any value in the vacuum is okay. So Maxwell theory in 3 dimensions is actually the same thing as saying you have an S1 sigma model. So a particle, a massless particle that can be interpreted as a Goldstone boson for this magnetic symmetry. All right, this is very different to what happens in 4 dimensions, but in 3 dimensions, this is what happens. Okay.
Sorry.
Yes.
Can I ask a terminology question?
Yeah.
This word disorder operator for the monopoles.
Yes.
They are genuinely local operators.
Yeah.
Disorder have like a topological.
No. They're local operators. Disorder just mean that the way to define them in this presentation is not via some combination of the fundamental field, as opposite to what happens here. I can write a formula in terms of sigma. Here I cannot write a formula in terms of A. Sure. And disorder means a boundary condition in the
so like disorder operator is the easy model where there is
topological line. No topological line. Here is they're genuine local operator.
Yes. In 4 dimensions, you need this operator.
Exactly. In 4 dimensions, there will be lines, right? Because I mean, in 3 dimensions, if you want to wrap a point, an S2 wrap a point in 3 dimensions, but an S2 wraps a line in 4 dimensions. So instead of being monopole, there will be Toft lines. Yes. All right. Now let me go to the second ingredient, that are the fermions. So we discussed the gauge field. So the fermions, okay, this is the Dirac-Lagrangian, okay, which describes fermions. You have the kinetic term, which is psi bar d mu psi. Then you have some mass that you can add, and then you have the coupling of the current to some external field, gauge field for the U1 symmetry. Okay. So what are the symmetry of this system? You have the U1 global symmetry that just rotates the fermion. Okay. Then you have charge negation, but okay, we'll not be interested in that. And then you have time reversal. And the time reversal, most importantly, in 3 dimensions, is only there if you consider massless fermions. If you consider massive fermions and do time reversal transformation, this is not a symmetry. Roughly because if you take psi by psi, time reversal transformation, this goes to minus psi by psi. Right? So if you add this term to the Lagrangian, the only way to have time reversal is to put m equal to 0. Okay, so let's focus to the massless case. Okay, and what happens is that, okay, this is like a more technical point, is that these two symmetries, that are good symmetries of my theory, have what is called a mixed Toft anomaly. A mixed Toft anomaly means that if you try to couple your system to both the grounds for the U1 and time reversal, you cannot preserve both at the same time. Okay?
And background for T means nothing.
Well, in my case, yeah, for discrete symmetry, you don't really do it like this. You just switch on the ground for U1 and do a time reversal transformation of this theory with the A mu on, and you will see that it transforms non trivially under T. Okay. So the point is that your theory is defined in 3D, and it has this anomaly. Anomaly means that actually the theory, in order to be well defined, it should be attached. You should think this 3D theory as the boundary, this manifold M3, as the boundary of some X4. Okay. And on this X4, there is an action, which in this case is just this one. And the total system is so-called anomaly free. But the strong point of this anomaly is that it is invariant under a normalization group flow. So you compute it in the UV, and then in the IR has to be the same. So even if the IR is strongly coupled, you have something that constrains the dynamics of the theory. Okay, now what I want is a theory that is time reversal invariant. So, and I want a theory where U1 is a gauge field, it's like a real photon. Okay, so since I have the mixed anomaly, I cannot gauge U1. If I gauge U1, I break T. Right? So if I want to preserve T, I have to cancel this anomaly. But this anomaly is a Z2 anomaly. Basically, each fermion contributes with this factor in the action in the bulk. So if I have an even number of them, since this is Z2, the sign here doesn't matter. I can choose plus or minus. So if I have 2, I choose plus for 1 and minus for 2, and I trivialize this part here. Okay. So the bottom line is that in order to preserve time reversal, I need to have an even number of fermions. And this guy is not important anymore. Okay. Tell me if I'm losing someone or everyone. Okay, now I'll put all the two things together. Okay. I will put the fermions and the gauge field, and I will write the Lagrangian that you see there. Now the things are coupled, and I think NF to be arbitrary. So as I told you at the beginning, if NF is very large, I know that the theory goes to a conformal field theory, is scale invariant. And the reason why it's so is because you can do exact computation in the limit where the number of fermions is large. It's like a perturbation theory in 1 over n. 1 over n is small, like a coupling constant. I can do perturbative expansion. And at leading order in this perturbative expansion, I can compute exactly the two-point function, the correlator of the gauge field. And this shows both in the UV and in the IR, so at short distance, at long distance, a conformal behavior. And this allows to conclude that there is a non-trivial strongly coupled CFT in the infrared, and you can do a systematic 1 over NF expansion of this CFT. But now, at some point, this CFT will stop. You will find this NF star, and the CFT will disappear. So the question is, what is the fate of this theory in the infrared? And as I said, the bootstrap analysis suggests that there is a CFT for any number of fermions smaller or bigger than 4, but they also suggest that NF equal to 2 is not a symmetry-preserving CFT. So now the question is what it is.
You cited my paper, but I don't think any of these papers that's concluding is that strong.
No, but okay, yeah, this is just
That's why you see.
it's just a sample of.
It's much weaker than that. We don't know what can happen. It's critical in that.
No, but I'm saying there's also the paper by Shai and friends that seems to be convinced.
Yeah, we roughly speaking know that the critical in F is before 8, blah blah.
Yeah, okay. No, but here, indeed, I'm not. I don't want to make any claim here.
Yeah.
I'm just saying, okay, let me assume that an F equal to 2 is not a CFT, and let me say what happens in this case. And well, okay, if I have time in the end, I will show you also that this is compatible with supersymmetry, but only if I have time. Okay, so I will focus on the easiest case. So instead of talking about generic NF, just an F equal to 2. So first of all, I will tell you what are the kinematics of the model, so the symmetries and the anomalies, something you can see with naked eye in the UV. Then I will show you what is our scenario, our proposed scenario for an F equal to 2 case. And I will try to argue how we got to this scenario by using some tools from Toft anomaly matching, mass deformation, and non-perturbative constraint coming from the so-called Vafa-Witten theorem. And then finally, if I have time, as I was saying, I will show you how this is compatible with supersymmetry. Okay. Okay, the Lagrangian is the same I wrote before, just an F equals equal to 2. And now you can ask, the first question we have to ask is, what is the global symmetry of the system? And well, naively, you would say that, so you have fermions, right? Fermions that under SU2 will transform like this. So if you consider the center of SU2, just the -1 element here, right? So the center will act like this. Right? But this is the gauge transformation. This is the same as the gauge transformation is like this. So if I choose alpha equal to pi, this is the same minus sign as here. So naively you would say, oh, the symmetry is not SU2, because I have to consider gauge invariant operator. The symmetry is SU2 mod Z2, which is SU3. Okay, so this is true as long as you consider operators that are only built from fundamental fermions. But actually, the magnetic symmetry that I was telling you before is still there in this theory because the Bianchi identity is not spoiled by the presence of matter. And what happens is that, so if you consider no monopole operators, so operators that have a monopole charge 0, they are indeed a representation of SO3 because of this argument here. Okay, but for instance, the hero of our story will be this operator here, okay, which is in the adjoint of SU2. Is the triplet, the triplet representation of SU2, which is the representation of SO3. Instead, if you consider monopole operators, which mean that they are charged at the magnetic symmetry, they can actually be in a genuine representation of SU2, which are not representation of SO3. And in particular, the fundamental monopoles, it has been shown by these authors, Borokov, Kapustin, and Wu, that they are in the fundamental of U2. And U2 is the global symmetry group. So you have SU2 flavor, you are magnetic, and Z2. So the monopole in the theory with fermions acquires some flavor charge, which they didn't have in Maxwell theory. Okay, so the fundamental monopole is Mi, and by the same argument, the pi element in U1 is identified with the center of SU2, and this is where this quotient comes from. And then on top of this, you have charge conjugation and time reversal. Time reversal because we chose the number of flavors to be even. Okay, now the same story as before. You have actually a mixed anomaly between U2 and time reversal. Exactly as for the free fermions, you had a mixed anomaly between U1 and time reversal. And this mixed anomaly can be written exactly like the second Chern class of U2, which is nothing but the Hamilton number for the U1 part and the SU2 part. Now, as I said, the anomaly must be matched along the normalization group flow. So this means that in the AR, this theory cannot be gapped, cannot be trivial, because you need some degrees of freedom to match the anomaly. Right? So already is a kinematic argument is telling us that the theory must do something non-trivial, because otherwise this anomaly wouldn't be matched.
Let's play the symmetry break.
Yeah, of course, exactly. But symmetry breaking means that there are gapless degrees of freedom, which are the Goldstone boson, or it's a CFT, so there are gapless degrees of freedom.
There's no TQFT you can
Good. No.
opposite the anomaly.
Yeah, as you say, there is a third possibility to match the anomaly, which is you have a gap, and below the gap you have a non-trivial topological field theory.
Yeah.
But this cannot match the anomaly because of a technical reason, because this anomaly survives, for instance, if you choose the SU2 subgroup of T, of U2. You just have this part here. Yeah. But if you have a simple, simply connected gauge group, you cannot match the anomaly with the QED because of some problem of fractionalization of angles. And so only for U1 symmetry, or only for abelian symmetry, this is possible. Or for groups that are more complicated than SU2. But for simply connected, you cannot. So this already is a bit stronger than the usual, right? Because sometimes you say, okay, no, that can be a TQFT. And in this case, this cannot be. So the kinematics just tell us, already tells us that something must happen in the AR, which is not surprising, but it's nice that you can prove this. Okay. So of course, we are not the first one to analyze this theory. This theory has an extremely long history. And I want to just summarize the two main proposals that were put out in the literature as what does this theory do in the infrared. So the first proposal dates back to Pisarski in the 70s. And the proposal is that you consider the bilinear of fermions, which is the time reversal invariant, because this one, psi bar psi, is the singlet, is the time reversal odd. But if you consider psi bar sigma psi, so these are the Pauli matrices, this can be made time reversal even. Okay, so the proposal is that this guy condenses, it acquires a vacuum expectation value. And so the SU2 or SO3 part of the global symmetry is spontaneously broken to the Cartan, to the U1 Cartan subgroup. And this leads to an S2 sigma model, right? Because you have two Nambu-Goldstone bosons. You go from rank 3 to rank 1. But then this proposal is not clear what happens for the magnetic symmetry. Is it broken or is it unbroken, right? What about the anomaly if it is unbroken? What about the additional Goldstone boson if it is broken? And if it is broken, which monopole operator is condensing? So all these questions were left unanswered by this proposal. And the reason why this proposal didn't take much space in the literature after it came out is because there was another proposal like 10 years ago that used a web of boson-fermion dualities in 3 dimensions to propose the following. So the idea was that the theory actually flows for CFT, but this CFT not only has the full U2 global symmetry, but is a so-called self-dual, and in particular, the global symmetry is enhanced. SU2 times U1 is enhanced to SU2 times SU2, which is SO4 times the Z2 that exchange them. So the proposal was that the theory is an O4 fixed point with O4 global symmetry. And as I said, there are some bootstrap results by Lee and other collaborators that show that this fixed point for QED does not exist. And as we need some degrees of freedom to match the anomaly, we need to have some symmetry breaking of the global symmetry of the U2.
This one can be embedded into the SO5 story.
Yeah, the SO5 is for a scalar QED, I think.
Yeah, the CP1 model has SO5 story, but I think it's you can break the SO5 into O4. Will that correspond to this one?
But isn't the SO5 the CP1?
Or it,
And CCP1, yeah.
So it's like trivially without introducing anomaly.
Right. No, exactly. So yes, the point is that if it is correct that there is no CFT, what should happen is that this RG flow actually doesn't go to a fixed point, like it runs.
But I think the SO5 the story can the CP1 model can be gapped because there's something called chiral spin liquid that people propose. That one can be gapped. If that one can be gapped, I don't see why.
No, this one cannot be. This theory cannot be gapped, right? Because of the anomaly. There is no way to gap this theory because there is a mixed anomaly that will prevent you to gap.
Okay, let's talk about that later.
Okay, so this proposal was very popular, saying that using this web of boson-Fermi dualities to show that if there is a CFT, then it has an enhanced global symmetry. But for the purpose of this talk, I'm going to say, okay, if this is not the answer, what is the answer? Okay, so the answer that we propose is the following: that the symmetry is broken, but not by the fermion bilinear, by the monopole that is condensing. And if you are familiar with the standard model of particle physics, this is exactly what happens in the standard model, because the Higgs field is exactly a doublet of U2, because it is a doublet of SU2, and it has some hypercharge, and then SU2 times U1 is broken to the electromagnetic subgroup. Here it's exactly the same, but it's not a gauge symmetry, it's a global symmetry. So the three Goldstone bosons are actually Goldstone bosons, and so you will end up having the quotient U2 times U1, which is just the S3 sigma model. Now, there is a very convenient way to parameterize S3, which is the Hopf fibration. So roughly, you will have the monopole is condensing, so it's parameterizing points on S3, and V squared is the VEV of the vacuum expectation value of this monopole. Then you can construct a projection from the sphere S3 to the sphere S2 in the following way. So at any point on S3, you associate this unit vector from S2 with this way and dagger sigma m. And this m is now in the triplet in the joint representation of SU2, but is not charged under U1. Okay? Now you can do the opposite. So given m, how do I reconstruct m? Well, you can reconstruct it uniquely up to the fibration, the fiber, the S1 fiber, which is made with some field which is 2 pi periodic. Okay, so basically I'm representing the sphere S3. S3, I think about S3 as a S2, and this S2 is parameterized by n, which is a unit vector on the sphere, and at each point there is a fiber, there is an S1, which is parameterized by sigma, right? By this sigma that goes from 0 to 2 pi. So, but S3, of course, is not S2 times S1. And so when you write the metric, you will have the S2 part, the S1 part, which will be sigma squared, if it was S2 times S1. But then there is also this fibration here that tells you that it's locally S2 times S1, but not globally. And this alpha is just the alpha is just the volume form on the S2. Okay. So this is the proposal. So you have a monopole condensation, exactly like in Maxwell. You have U2 that is broken to U1. You have 3 Goldstone bosons, and you have an S3 sigma model. This is very useful to distinguish what is what is adjoint breaking. So the S2 is really the S2 that Pisarski was talking about. Like the fermion bilinear is breaking psi bar sigma psi to U1. But also on top of this, you have the dual photon that gives you the fiber. Okay. So yes, this is the method, and sigma is the photon.
So once you have this breaking pattern of the single charge monopole that condenses, can you not further condense the fermions in a way that still keeps this U1, or there?
Very good. I'm coming to this in 30 seconds. Yes. Okay. This is the picture. Let me make an example to understand what is the importance of the fibration. The importance of the fibration is that the U1 that is preserved depends on the point on the sphere where you are at. So let's do a simple example. Let's take as n the z-axis. Okay, so the North Pole or the South Pole. So if you have a monopole at the North Pole, under the Cartan it is charge +1. If you have the monopole at the South Pole, under the Cartan is charge -1 of the flavor symmetry. But the monopole charge is always 1 for both. So at the North Pole, if you consider that M and F are both 1, you see that under the plus combination it has charge 1, and under the minus combination it has charge 0. And this means that at the North Pole, the symmetry that is preserved is the anti-diagonal of magnetic F flavor. But if you go at the South Pole, it's the opposite, right? And this is the hallmark of the fibration, right? It depends on the point where you are. Now, let me come to Antonio's question, which is, okay, what about the fermion bilinear? So what we propose is that also the fermion bilinear is condensing, but it's condensing in a way that is aligned with the Cartan that is already singled out by M, right? So this guy condenses. What you will have is something like this. And the claim is that the fermion will be parallel to this, will be proportional. And I will show you why this has to be the case. So basically, if they were not aligned, you will have further symmetry breaking, right? The U1 will be still broken again. But I will show you that this cannot happen. So it has to be aligned. Am I going faster or going slow? Okay. Okay, the last point I want to make is that what happens if you have a small mass deformation? So a small mass deformation is just you have the triplet to the Lagrangian with some mass, which is some vector. And because of what I said, that under the RG, this guy just becomes n. This deformation looks like this. So this is like I add a mass, and I'm asking myself what happens to this vacuum. And what happens is that the mass deformation will select the n, which is parallel to it, to minimize the energy. So this means that in the massless case, you have the full S3, but as soon as you give a mass, the S2 will be lifted. So you will just have one point on the S2. Which one? The one such that its vector is parallel to the mass that you gave. And so, but on that point, you will have some S1 that is not lifted. Okay? And this is very intuitive. You give a mass to the fermion, what you are left with is Maxwell theory, right? So you're just left with a circle. Where? Well, it depends where you are. Okay? So this means that as soon as you give a small mass, you get a Coulomb phase parameterized by the dual photon, and the CP1 base, the S2, is completely lifted. Finally, I have to tell you why this is compatible with anomaly matching. First of all, U2 is broken, but charge conjugation and time reversal are unbroken. And we can prove that time reversal is unbroken using the Vafa-Witten theorem. And of course, the anomaly needs to be matched. And the way it is matched is a bit subtle. So S3 has a third homotopy group, which is given by the integers. This means that it admits a theta term. A theta term you can write in this way, in the Lagrangian, just an integral of the space-time, and U is just the matrix of those bosons. And if you perform a time reversal transformation, only theta equal to 0 and theta equal to pi are invariant under time reversal. 0 is nothing, but it turns out that theta equal to pi matches the anomaly. How do you prove this? Well, you take this action, you couple to a background gauge field for the U2, and you see that this action, once coupled to this background, just becomes this. And if you remember, this is exactly the formula for the anomaly here. Right? So in the UV, you have this anomaly. And in the IR, if you add a theta term, you have this. So to match them, you choose theta equal to pi. Okay. Okay, so this is our proposal, and now I will try to motivate how we get there. Okay, so you can forget about it, and now I'll try to construct it. Okay, so the first thing you can do. So let's go back to the UV Lagrangian, right? So we go back to the UV Lagrangian, we say, okay, we cannot do anything. The theory is strongly coupled. How do we proceed? So one known corner of parameter space where you can apply perturbation theory is when the mass of fermions is very large. Then you can use a perturbative expansion. And after speaking, the 1 over the mass will be the perturbation, well, E squared over the mass will be the adimensional perturbative guy. And so what I do is the following. I take the Lagrangian, okay, and then I couple the Lagrangian to the magnetic field for the U1, but also I choose a Cartan direction. For simplicity, let me choose sigma z. And I also couple the current of this, which is psi bar sigma z psi, to A. So AF is the background field for the flavor symmetry, and AM is the background field for the magnetic symmetry.
Sorry.
Yes.
So can you just tell me? So in the m equals infinity limit, you know what it is
Yes.
in the IR.
Yes.
Can you tell me clearly why this perturbation theory is directly to like what is the intuition?
The intuition is that, I mean, if you have a large mass, like the propagator is frozen, basically.
Yes, but we know already what is the theory in the infrared and stick.
Right.
Okay. And
I want to tell you how this is now connected to the proposal.
okay.
I want to show that you can see the vibration also in perturbation theory, actually.
Okay.
So what do we do? So we have this Lagrangian coupled to this background, and then I add the mass. The mass that is aligned on the same z direction, right? So it's the mass that gives mass plus m to psi1 and minus m to psi2. And then I integrate out fermions. So when you integrate out fermions, you will have that the fermion part of the Lagrangian disappears. So we just have the Maxwell part with a coupling that is possibly normalized by integrating out, since it's a function of the mass. Then you will have some irrelevant term like Euler-Heisenberg Lagrangian. And then you will have this guy will stay, okay? But when you integrate out this, you will generate a mixed Chern-Simons term between the gauge field and the AF. And you can do this computation, and what ends up is that the level is just the sign of the mass. Okay? You're just computing this diagram, basically. A mu here, fermions, and here an insertion of the J current. When you compute this, you will generate this mixed Chern-Simons term. Right? We are used to the fact that when you integrate fermions with the same mass, you generate a Chern-Simons term for the gauge field. Here, this does not happen because there is time reversal. But what happens is a mixed one between A and AF. Now you see, and now I ask you, okay, what is this theory? Well, this theory is just Maxwell. But the monopole, which is the configuration such that the A over 2 pi is something, under which U1 is charged. Well, it depends where you are. If you give a positive mass, it is charged under the plus combination. So the plus combination is broken and the minus combination is unbroken. If you give a negative mass, it will be charged under the minus. So the minus combination is broken and the plus is unbroken. But this is exactly the same as we conjecture here, no? The small mass regime was exactly the same of U1 plus and U1 minus condensing or being preserved. Okay? So at large mass, this can be proven. And this is exactly what happens. So you can see that this Chern-Simons term is responsible for the vibration. Now the question is, okay, this is for very large mass. What happens when you lower the mass? So what I'm now going to argue is that you will not encounter any phase transition when you go to arbitrary small mass. Okay, I'm going to argue this by using some theorem. Okay, let me say first that okay. So the hero of the story are Chern-Simons term, right? And Chern-Simons terms are quantized. they cannot vary continuously in perturbation theory. This is a theorem proven by Coleman and Hill in the 70s. So that as long as you are in perturbation theory, you will never see a jump on this Chern-Simons term. But now we want to be a bit more strong. We want to say that you will not have any jump, so not even in at non-perturbative level. And the key argument to understand that why there cannot be any jump is that in order to have a jump, since the Chern-Simons is the Chern-Simons that involves the gauge field, you need to have massless matter that is charged under the gauge group. Right? So you need something that makes this transition to the Chern-Simons level but has gauge charge. And then the nice thing is you can prove this inequality exactly for any value of the mass, which is the following. If you take any operator with gauge charge Q, okay, and then at point X, and then you take O dagger at point Y, and then you put a Wilson line to make it gauge invariant, this correlator is always exponentially suppressed with the mass for any finite mass, not for any infinity, right? For any finite mass, you can prove this, and this is what we do. And whatever the operator O is, as long as it has a gauge charge which is different from 0. What does it mean? It means that no way at any value of m, there is something that can become massless if it is charged under the gauge group. And if you think about it, it's very intuitive, no? Because what does it mean to have an operator which has gauge charge? In an abelian theory, it means that inside it is made of electron, right? Not electron, anti-electron. But in an abelian theory, there is only the Coulomb channel. There is no, like in an abelian where they have the singlet, the joint that can be repulsive or attractive. In the end, Coulomb repulsion is repulsive. And so the bound state is disfavored with respect to the repulsion. And you can make this precise by this inequality here. And so you have a charge gap. So any matter that is charged has a mass. And this means that the behavior that we found for very large mass with this vibration of the monopole actually has to persist to all masses, as long as they are different from 0. Okay? So the argument is nothing charged can become massless, so the Chern-Simons term cannot jump. Now, when I say it has to persist smoothly, I'm a bit cheating because I cannot exclude the possibility that some neutral stuff actually becomes massless and you have a phase transition, but this will never interact with the photon. It will only interact, you can prove that it will only interact via irrelevant terms. So whatever this other sector is, you still have the photon with the Chern-Simons levels.
How do you prove it?
Well, it's just dimensional analysis, basically, because the photon is the only.
I mean, I understand you cannot write in a Lagrangian a term that interacts.
But this is everything is weakly coupled here. So okay, we cannot. It's basically any sigma model in d greater than 2 has only irrelevant interaction.
Mm-hmm.
That's the short way to understand. This stuff, even if it's there, does not destroy the argument. And so this goes through to all masses even different from 0. Okay.
Where is this one coming from?
Oh, well, this you can prove this using the Baha-Witten theorem. So you know that you have a restriction on the symmetry breaking, and you can prove some bound on the correlator. It comes from bound on the correlators from Fermi propagators. So in this theory, any operator that has gauge charge Q contains in its belly like psi Q times, roughly. There is no other way to make an operator that's charged Q here. The only charge object is psi. It has you can build this operator and then you start doing the big contraction, and you can prove that this has to be bounded. We didn't do the job, it was already there in the original paper, so we just used the bound.
I'm still a bit confused because so this is supposed to be a non-perturbative state.
Yes.
But you're just saying that you're proving it kind of perturbatively.
No, but the proof, sorry.
So the bound, I mean, the bound
is non-perturbative because this bound is valid regardless of A.
Okay.
And
but your perturbative regime is for large n.
Yeah, but I'm not introducing it here. I'm just I can show you later how to do it. But basically, you can bound the correlator, and this bound does not depend on the perturbative or non-perturbative regime. The only requirement is that you have a mass which is non-zero. Why you need this? Because you need the path integral measure to be positive definite in Euclidean signature, which is not the case if you have just free Dirac fermions without mass. And that's the reason also why we preserve time reversal, because to prove these theorems is absolutely crucial that you have time reversal invariance. Otherwise, everything that I'm saying doesn't hold. Okay. So this was to convince you that what I said here actually applies not only for very big M, but for all M that are not zero. Okay, the second ingredient I need is the Vapo-Witten theorem, which imposes constraint on the allowed pattern of symmetry breaking in time reversal invariant theories. For instance, if you apply this to the well-known theory of QCD in 4 dimension, it will tell you that time reversal cannot be broken, and also that the only allowed pattern of symmetry breaking is the one that we all know, that is parent symmetry breaking. If you apply this machinery to our theory, there is actually a subtlety, because maybe you would say, oh, the vector-like symmetry is the Cartan U1F of SU2, and this has to be unbroken. But what can actually happen is that there is a mixing between this Cartan and the magnetic symmetry. And we already saw the mixing that was playing a role here, right? The mixing the plus and the minus. Now, long story short, if you apply these arguments to QED, what you conclude? First, you conclude that time reversal has to be unbroken. This is very important, because remember that the anomaly that I used to guide me is a mixed anomaly between U2 and time reversal. If time reversal was broken, then I could say that I don't know what happens to U2. I could match the anomaly by breaking time reversal. But this I cannot do, because time reversal has to be unbroken. So something has to happen to U2, and these arguments tell us two things. They don't tell you what is the alternative that is realized, but tells you if there is no monopole operator that condenses, you have both symmetries that are unbroken, the Cartan and the magnetic. This, if you want, is the Wizarski proposal, right? The SO3 goes to U1, and then there is the magnetic there. If some monopole operator condenses, which has some charge, QM and QF, then you have some linear combination of the two U1 that you get in this way that must be unbroken. And this is the explanation of Antonio's question that say, okay, how do you know what the fermion bilinear does? Well, if it was not aligned, I could not preserve this, but I must preserve this. Okay, now we put everything together and we list all the possibilities to what happens to the theory. So, first option is that you have a gapped phase. So you have nothing and then a mass gap. And as I said, this is incompatible with anomaly matching. It cannot match the anomaly. But it also is incompatible with the statement that I made that as soon as you give a small mass, you should find a photon. Of course, if you perturb nothing, you will never find a photon. So we have two arguments that exclude this. Then you can have a CFT with at least due to symmetry, and this I cannot exclude. This can happen. I'm saying this is implausible. Let's see what happens, because I want to stay outside the conformal window. But of course, this would be the alternative that is realized if this NF star would be actually smaller than 2. Then there is the original Wizarski proposal that was saying, okay, the U2 is broken to U1F, and the U1F is preserved. And this gives rise to two Gauss-Cohn bosons, so an S2 sigma model. You have only the base. You don't have the fiber, the photon. But this is incompatible with anomaly matching. Why? Because you can gap this theory. This theory, you can gap it with a mass. And as I said before, the mass just lifts and selects a point. But then you will still have an anomaly for the broken subgroup. This guy still has an anomaly with time reversal. And this cannot be matched if you just have a point, right? So this cannot be the answer. So anomaly matching may say, look, it cannot be only S2. It has to be S2 times something that matches the anomaly. Now there can be something. Before, your question was, well, why cannot match it with a topological field theory? Because it was an SU2 anomaly. Now it's just an anomaly for U1 times U1, so we can have a topological theory that matches it. But now this scenario is incompatible with the Coulomb phase. Because now I give a small mass to this, what happens? The S2 is lifted because it gives a point. But then I'm left just with T. But T is not Maxwell theory, which I should find.
So it's essentially your definition of, it's kind of a requirement in a sense.
Yeah, exactly. So the non-perturbative requirements are, I give a small mass, I find Maxwell theory, no matter how small the mass is, and I need to match U2 T mixed anomaly without breaking time reversal. And then listing the possibilities. The last possibility is what we're claiming is what happens. So U2 is going to U1, and you have 3 Gauss-Cohn boson. This is the scenario that we proposed, as I said, was also proposed at the same time by the other authors. And this is compatible both with anomaly matching, because we will have a theta term at theta equal to pi that matches the anomaly, and the fact that you have a Coulomb phase as long as you give a mass, because it's what I showed before. Okay, I have 5 minutes. So I will not talk about supersymmetry. Okay, this is their work, so maybe we can skip it. Okay, a few words about supersymmetry, or we can just end here.
You can
Flash.
yeah. No, so if you can summarize a bit again.
Again, the story. Okay.
For
Okay.
example, can you tell me again why you cannot exclude the darkness space just because you don't have the CFT?
Yeah, because the CFT is compatible with all scenario, all constraints. I'm saying that the CFT is compatible.
Okay.
There is no analytic way. I wanted to try to propose you a way to exclude the CFT using supersymmetry.
I see.
But I can just sketch it very briefly.
Yes.
Very briefly. There is a very complicated theory. Okay, this is the Lagrange, but don't even read it. This theory has a photon, scalars, BG, charge scalar, and fermions. Okay, this theory is here in the UV. Okay, this theory is in the UV. It's called the animal for super QED. Okay, then the IR of this theory is known. It has been worked out by Cyberg and Witten, and is basically a Coulomb branch, okay, a 4-dimensional Coulomb branch. Okay, this is known. What I'm doing here is that I'm deforming this theory in a controlled way that can be mapped into the IR using conserved current, basically stress tensor multiplets. And this, if I do this deformation, I'm getting rid of this guy. So I will just end up with the theory I want, which is QED3 with 2 fermions. When I do the same thing here, what happens is I get an F3 sigma model, which is the thing because the metric on the Coulomb branch, we don't need to do anything. Cyberg and Witten computed it for us, is this metric here. And you see that once you fix a point on the Coulomb branch, this just becomes the S3 metric. So this is suggestive that our proposal is actually correct for an F equal to 2. The theory does not flow to a CFT. Now, if you start with a theory with more hypermultiplets that is supposed to go to QED with not 2, but generic NF, you will start seeing that for any NF that is not 2, 4, 6, 8, the Coulomb branch has a singularity at the origin. And usually when you have a Coulomb branch with a singularity, it means that there is a massless degrees of freedom lived there. So it's very suggestive that supersymmetry tells a difference between an F equal to 2, where the Coulomb branch is smooth, namely R equal to 0 is not a singularity of this metric, and an F greater than 2 when actually there is a singularity, so it's suggestive that the theory wants to do something else. Of course, this is very brief, but we have a supersymmetric construction to try to go a bit beyond this. Okay, I think I'm out of time, so I leave the conclusion here. No, I have 3 minutes. Okay. But okay, I mean, so okay, let me summarize in a second. So what we show is that the symmetry breaking in QED is driven by monopole operators, which carry both magnetic and flavor quantum numbers, as opposite to what happens in ordinary 4-dimensional theory, where it's only driven by fermion bilinear. So our proposal is that using the Vafa-Witten theorem, Toft anomaly matching, and the small mass deformation, we think that we can give strong evidence that if the theory does not flow to a CFT, then you have spontaneous symmetry breaking of U2 to U1, you have the condensation of the monopole, and this gives rise to an S3 sigma model with a theta equal to pi term that matches the anomaly. And one of the non-Goldstone boson is always the dual photon, is also this circle, and this generalizes to any NF. So I wrote here the pattern of symmetry breaking. Instead of being U2 to U1, is UNF to SUNF over 2 times UNF over 2, okay, which for NF equal to 2 is exactly this. Okay, but you can generalize, and the tricky point is always that the Cartan of this will mix with the magnetic. Due to the vibration, it will give an unbroken subgroup, which is always a mixture of the two. And this scenario is consistent with supersymmetry. And as I was saying, if you have more hypermultiplets, the Coulomb branch will have a singularity. So there is a hint from supersymmetry that you have a CFT-like behavior if that is 4 or greater than this. Okay, I didn't talk about the first point. Of course, we can do many other things. So for odd and F, this will be much more difficult because we lose time reversal. You can action trimester, or even you can have other interaction channel like for non-abelian gauge theories. And then maybe we can find the evidence for this non-CFT behavior in some lattice system and in some cases of math. Okay, thank you.
Thank you so much. Okay, so is there any question? One?
Yeah.
These two condensations, do they need to happen at the same time, or one could, is there some constraint probably the monopoles need to condense first, or you're saying as we can done there before?
That's a very good question. I think it's related to this fact is that you see that I don't write S3, I write S3 tilde. What do I mean with this? I mean that it's a squashed sphere. It's not a round sphere, because the two, if I write the metric, the S2 part of the metric has some radius r squared, and the fiber has some other radius e squared. So if the two were equal, this would be a round sphere, but we have no reason to suspect that this is a round sphere. What is that? If it was a round sphere, it would have O4 symmetry, right? Which kind of sounds, but we don't have any reason to believe that these have to be the same. And my guess is that both of them will be functional, which is the only scale in the problem. But this will be the scale of the fermion bilinear condensation, and this will be the scale of the monopole condensation. But there is no way to know what are these numbers, right? This is a number times e squared, but nobody knows how to compute this. Of course, it's an extremely strong coupling problem. Yeah.
Well, thanks again, Pierluigi, and we are going to have a 15 minutes break, and we will see.
Okay.
Okay.
Thank you.